Welcome to another video on digital electronics. In this video, we'll be starting with the module 5, that is analysis of sequential circuits. So before moving to any of the numericals, let us understand the concept of what is sequential circuit and what are different types of models which are used in sequential circuits. So sequential circuits, as we know, work in some sequence, that is they move from one state to another state, and that is represented by a state diagram like we have seen in counters, right? So similarly, I can have any kind of a sequential circuit. There are various models which are used in sequential circuit. One of those models is called as a Mealy model. If you look at the diagram here, this is a diagram for the Mealy model. It has got three different things. The very first one is called as next state logic. Since this is logic, it is understood that it is using some of the gates to create those logics. So this is nothing but your combinational circuits which you have studied using gates. Similarly, you have output logic. This is also logic, and hence this is also using gates. So I'll have some combinational logic here using gates. And this is your memory element. Where have you studied memory element? Of course in flip-flops, right? Where one flip-flop stores a single bit of memory, that is one bit of information, either a 0 or a 1. So I'm using this memory element here. Now what happens whenever I have a combinational logic at the next state logic, which will help me create the next state. So I'll have some external input coming to this next state logic, which will create some output that goes to the memory. It's there in the memory, it saves there in the memory, and this helps you create the output logic. This output of the memory goes as a feedback to the next state logic. Like in the counter, if you remember, we did counter counts 1. I have a flip-flop, 1 gets stored there. This 1 comes as a feedback to the external input that I am applying, which is nothing but a clock pulse. With one more clock pulse, this 1 will change to 2. This 2 will again come as a feedback, and I have one more clock pulse which is incrementing this to 3, and so on and so forth. So it is something similar to this. In Mealy model, your external input is also directly applied to the output logic. So that's the difference between Mealy and Moore model, which we'll be seeing immediately after this, right? So you have to understand that external output is directly influencing your output logic. Next state logic will give the output of whatever the value is to the memory element. Memory element will save it, create a output logic from where you will get your final output. This will come as a feedback to the next state logic, right? And memory uses flip-flops, whereas next state logic and output logic uses combinational circuits, which is nothing but your gates. Now come to the equations. Next state logic is a function of the present state that I am applying to it and the inputs. The present state is in the memory, so present state comes as a feedback, and the external inputs that I am applying, that is what the next state logic is a function of. Output, on the other hand, is also a function of the present state. Present state is always in the memory, right? Is also a function of a present state, and is also a function of the external inputs that we are applying. And hence next state and output both are a function of present state and inputs in this case. When we move on to the Moore model, the only difference that you see between this Mealy model and the Moore model is that your output is no longer dependent on your external inputs. This is not happening. So what do you have? Again, you have an next state logic, which is your combinational gates. This is also a combinational gates. This is your memory element, which is flip-flops. You have the present state coming back to create the next state logic. Now what are the functions? The next state is a function of the external inputs and the present state from the memory. But now output logic is only and only function of the present state. There is no input over here. So it is not a function of external inputs that we are applying. This is what you have to understand between Milli model and Moore model. So the systematic procedure of the design of clock sequential circuit is based on the concept of states. What are these states? The next state and the present state. For these circuits, the sequence of the inputs, that is present state and the next state, and the output can be represented by a state table or a state diagram. The combination of the present state and the external input results in a transition to the next state when the clock is applied and an output, right? So this is the combination of present state, which is in the memory, and the external inputs, which is coming from here, will result in a transition to the next state. From the memory and the external input, I will get a next state, and depending on this, I will also get a external output, the output logic here. So this is your present state and this is your next state. When I apply a clock pulse to the present state, I will move on to the next state. This exactly is represented by something called a state diagram and state tables. So the above operation of the clock sequential circuit can be described in the form of a diagram, which is known as a state diagram and a state table. So this is my state A. Currently my circuit is in state A. After giving a clock pulse, I will move to the state B, right? So these are called as nodes. A and B are called as nodes. What is this 1 and what is this 0? If I'm in state A, if I give input 1, I will move to state B and my output will be 0. So this is nothing but your input and this is nothing but the output that you get. So the circuit is in state A and an input 1 will cause the circuit to make the transition to the state B. I will move to B and this will give me an output of 0. This is the most simplest possible diagram having only two states. I can have multiple states together, which will be seen. So for example, I have a question, draw the state diagram of a D type flip-flop. So I have a D flip-flop here. Since this is a flip-flop, this stores only one bit. One bit has two combinations. Either it could be 1 or it could be 0. So I'll have two states. My circuit is either in 0 or in 1. So now we have to look at the truth table to do the state diagrams. So my first combination is I am in state 0. If I am in state 0 and I apply a 0, I will remain in state 0. If I am in 0, I apply a 0, I will remain in 0th state. To D flip flop, if I am in 0th state and I apply a 1, I will move on to 1 state. If I am in 0, I apply a 1, I will move to 1 state. If I am in 1 and I apply a 1, I will remain in 1. So I will remain in 1 if I apply a 1. If I am in 1 state and I apply a 0, if I apply a 0, I move to the 0th state. So I will move to the 0th state. This is how we represent the state diagrams. Now coming to state table, say this is one of the state diagrams that I have. From this I have to write down a state table. Then how do we do? First of all, you have to check how many states do we have. 1, 2 and 3. So I'll note down present state A, B and C. I have 3 states. Now for 3 states, I have to check what are my inputs, my next state and my output. So if I am at A, I apply a 0, I remain in A. I apply a 0, I remain in A. My output is also 0, right? So let me just highlight this for a better understanding. If I am in A and my X is 0, my X is what? X is input. X could be 0, X could be 1. So I have two combinations. X could be 0, X could be 1. That is my input. And what are these? These are my next state and this is my output Y. This is my next state, this is my output Y, and this is my input. X is my input. So if my present state is A, I give an input of 0, I remain in A and my output is 0. I am again repeating, my present state is A, I give an input of 0, I remain in A, I get an output 0. If my present state is A, my input is 1, I go to B and my output is 0. Let's check. If my present state is A, my input is 1, I go to B and my output is 0. Similarly, we fill up this entire table. Let's do one more. I am in B, my input is 0, I go to C, my output is 1. If I am in B, my input is 0, 0, I go to C and my output is 1. So in this way we have to fill the entire state table. So this is just to make you understand that what is state diagrams, what is state table. From one, how can you make another one? From this, how can you make this? And for any flip-flop, how can you make a state diagram? So this was D flip-flop. Similarly, you can have any flip-flop. I hope the concept is clear. Thank you for watching.